knowing what you do. Now, with these applications, they're a bit easier. The only thing that might be difficult are terminologies. And then once you've got the terminologies right and you use the right formula, it's all easy. Yeah? Sorry? Yep, it's recording. Okay, so Exercise 5I applications. Let's start off with like your general exponential applications problems. Yeah? Now, exponentials, we know usually you have something like 2 to the power of x plus 1, for example. True? Now, 2, the base, we understand that the base dictates what's happening to the issue. Now, when you say 2 to the power of x, what's actually happening in that particular problem? What's happening when you say 2 to the power of x or 3 to the power of x? What are you actually modeling? When I say 2 to the power of 1, and then 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, what's actually happening? What are you actually doing? What's happening? Think about 2 to the power of 1, which is 2, and then 2 to the power of 2, 2 times 2, which is 4, and then 4 times... What's the next one? 8. So what's happening? 2, 4, 8, 16, 32. You're doubling each time. So when I ask you, what is the base 2 doing to the graph? Or what kind of model are you dealing with here? You're dealing with something that is doubling each time. Okay, and then so it has to have a problem where they might say, you know, a particular cell is split up into 2 every second. So what happens is, after 1 second I split it into 2, so that's 2. And then in the next second I split those 2 split up into 2s. So that now becomes 2, 4, 8, 16, 32. So in that particular model there, you would be using a base 2. True? Okay, because you're saying it's doubling each time. Because even though you're saying it's divided by 2, but you're multiplying, you're doubling the amount of bacteria or viruses you have. Another example would be when you're doing sort of banking and money. You know, so when you're talking about percentages, like if you bought a laptop, right? If you bought I bought this laptop, and when you're doing your taxes, you can figure this one out too. Let's say I bought my laptop and it reduces or depreciates in value every year. Okay, so if I said it depreciates by 3% every year, okay, how do I model this? What is depreciating by 3% actually mean? What are we doing? It becomes 97% because every year I'm taking off 3% of the actual value. So if this was worth $100, next year I've lost 3% of the value. It'll now be $97. But then the year after that, I'm taking 3% off the $97. And then every year I'm doing 97%. I'm only getting 97% of the value every year. So if you want to model this, if I were to say it's 3% every year that I depreciate, okay, you would be saying the base is 0.97. Why is it 0.97? Why is it 97?
Because it's the amount that it reduced to.
Yeah, it's the percentage. 97% is what I have. It's 90%, 97% of whatever the amount I had. So if I bought it for $100, you'd say the amount is $100 what I bought for, 0.97, which is the percentage that is left over after a certain amount of time. You see, if it was after 1 year, this would have been 1, and you would have said that means it's 100 times 0.97, which really just means 97% of 100, which makes sense why after 1 year, it's $97. But then if it's second year, I'm doing it twice. If it's the second year, you will be saying, I'm actually doing 97% of $100, which is 0.97. And then after that, whatever this answer is, I'm doing it again, times it by 0.97. That's why you have 0.97 squared, which means I'm taking 97% twice now. Okay? And so this is an exponential problem because it's 0.97, which is my base, to the power of whatever it means in this time. In this case, it means time, and the amount is depreciation. Okay, if I want to talk about growth, instead of losing an amount, let's say every year I gain 10% on the amount that I put in my bank. So if I put $100 into my bank, and they said, I'm going to give you 10% every year if you keep $100 in your bank, then it will be 1.1. Because 1.1 is 110%, because I'm getting 100% of what I already had with an extra 10%. Yeah, so 110% is the same thing as saying 110 of 100, which is the same thing as 1.1. In this case here, this would be modeling 1.1 to the power of x is the number of years I put into the bank where I get growth. Okay, so I get growth. So the base dictates how much value or what your problem is. And your today's exercise is to figure out what kind of problem I have, what will the base be, how does it change my exponential problem or not. Yeah, in my case, I was talking about depreciating in percentages, but sometimes it might just be a decay exponential. See, when you're drawing a graph for exponentials, this is a problem where you have 2 to the power of x, for example. That's an exponential problem where it dictates growth, right? But then you also have one where it's a decay, where it represents over time, I lose money. Now, how do I get this kind of graph? What kind of graph would that be? It'll be negative x, because it's a reflection in the y-axis, so this would be a problem where your reflection, it's a decay. Okay, so today's problem, I'm just going to go through some examples where you see the different types of wording they use, and you dictate whether you change the base or whether you change the time to replicate or model what you had. Okay, so are they doubling in bacterias? Are they depreciating in value? Are they increasing in value? Or in our case, we were talking about half-life before. It's after a certain time, what does it become after a half-life? Okay, so that's the 3 examples I'm going to go through just to get you thinking about them, yeah? This is what I want you to copy down. Here we go. Right there, I know they're using different letters there, but really it's the same thing as your exponential equation. This is your base. If they don't tell you what the base is, you will assume it is base E, Euler's number, okay? If A naught is telling you what you started off with, okay? They normally say amount 0, meaning the initial amount. Okay, but really that's just a dilation factor. Dilation factor of A from the x-axis. Okay, that's all it is. That's just telling you how much you started off with, and are you increasing it or are you decreasing that amount? Kind of like the amount that I gave you before. I said I had $100 for the laptop. Over the years, it depreciates by 97%. So I did 100 times 0.97 to the power of x. Yeah? In this case here, they're just using different letters to represent an exponential equation. A is the total amount, which is like your y value. A naught is like your initial amount. What are you starting off with? E, which is your base, unless they tell you what the base is, then you change it. Otherwise, we can take default as exponential Euler's number. Okay, an exponential graph, natural number. K, we don't know what the dilation factor of K is. It could be, increase or decrease, I don't know. It could be positive, could be negative, I have no idea. T, for time, over time. Okay, because most of the problems you deal with is over time. So, things to copy down here, when K is positive, so even before you read all these, if K was positive, what kind of graph do I have? K was positive. Yeah, it's a positive exponential graph, which explains why it's a growth of cells, or it's population growth, or whether it's continuous compounded interest if money is increasing. Okay, because it's a growth picture. This graph here would be an exponential graph where K is positive. So Y equals, I don't know, A naught E to the KT, where that's positive. That makes sense. It's an exponential growth graph. Whereas if K is negative, then what kind of graph would I have here? Negative graph, which is makes sense why we call it radioactive decay, or in this case, cooling on materials, the temperature dropping down. Something has to drop. It could be money value, it could be depreciating value, whatever it is. We just know K is responsible for changing it down. And that's what I'm saying. These are just properties of the exponential graph. So the better you understand the exponential graphs, you're just really trying to model. That's what applications are. Yeah? So in this case here, if K was negative, you have a depreciating graph. I don't know what normally you don't have negative time, so you ignore that left-hand side here. Yeah? Unless they tell you that there is negative time. So maybe ADC and AD and BD. Is that right? No. AD and BC. Yes. All right. Here we go. Let's do a quick problem where we change the base. So this is in your textbook, and it's just a term that I want you to copy down. They call it generation time. And I'll show you in the next slide what generation time actually means when they say it. I haven't seen it in your exams, but for the sake of doing this exercise for 5I, they'll use the word generation time. Okay, so here we go. Cell growth. So cell growth, we know that the K value has to be a positive. Now they're saying here, suppose a particular type of bacteria cell divides into 2, okay, new cells every T minutes. So after 2 minutes, then, after every minute, you lose, you not lose, but you get 2 extras. So you're doubling each time. That's why they changed the base to 2. Okay. Now TD is the minutes. Let N naught be the initial number. So how many bacteria you're starting off with? After T minutes, the number of cells N is given by. So this is the number of cells that you get after a certain time. Now my question is, why is it T over TD? Someone explain to me, what is TD? So TD says that it's for every minute. 2 new cells for every minute. Why is it T over TD? So if you just look at that, I'm interested in why this is T over TD. Someone explain to me. Because 2 makes sense. We're saying it's every 2. If they said splits up into 3 cells every minute, then you would change the base to tripling. Triples every time. So doubling in this case would be a base 2. Why is it T over TD? So why couldn't I just say N naught times 2 to the power of T? Perfect. The only reason why is because we don't know whether TD is for every 1 minute. I could say that maybe it splits up into 2 cells every 30 seconds. So then that changes problems, because if T is in minutes, then in 1 minute, there are 2 30 seconds. 2. So the only way to know that is you get 1 divided by 30 tells you you've got 2. So then 2 to the power 2 will tell you you've got 4. So without having that TD on the bottom, you're assuming it's always going to be for every 1 minute. You don't know if it's going to be every 1 minute. It could be seconds. It could be every 3 minutes. Okay, so if it's every 3 minutes, this will change. It will change the fraction. It will change the amount that you have. Okay, so the TD will dictate. It might not be for every minute. And that's where a lot of students will forget. They'll do 2 to the power of T, and they forget that you do need to be careful, because it might not be for every minute. Could be every second or whatever it is that you're working with. So the units matter. Okay? So now, last thing is TD is called your generation time. Okay, so if they use the term generation time, they're referring to how long does it take to split cells. That's what your TD is. Okay, and because of your generation time, we don't know. It could be every minute, it could be every 30 seconds, 20 seconds, I don't know. Okay? Now let's do this problem. Using the same thing that you have there. They're using N and N naught, but really you could use A and A naught if you wanted to. It's the same lettering, it's just, you just gotta understand what they're modeling. Okay? Now in this case here, what is the generation time? So they're asking you to find TD, generation time, of a bacterial population that increases from 5,000 cells, that's where you're starting, 5,000 cells to 100,000 cells in 4 hours of growth. So what I wanna know is, what is my generation time? Meaning, how much am I splitting every minute? Okay. Now this is assuming that, because we're talking about bacteria in this case, we're saying that it's base 2. Okay. Unless they specify it, otherwise it's base 2. Okay. So we know it's base 2. How are we going to solve this? What's the first thing I'm going to do? It's just applying what you see there. Give me 5,000. I've got 100,000, and I've got 4 hours of growth. And I'm trying to find TD. Whoops, whoa. I'm trying to find TD. What is equal to 5,000? What's equal to 100,000? And what's equal to 4? Someone tell me. What is equal to 5,000? What am I modeling here? Yep, so what would 5,000 represent?
Well, 5,000 would be in base 0.
Good, and naught?
Yeah.
Initial, because that's how much you're starting off with. They're saying increases from, so I'm starting at 5,000 to 100,000. So what would 100,000 represent then? N, because that's the final amount. So I've got N as my final amount, and then obviously 4 hours of growth, that has to be T. Yeah. So now that you've got one whole equation, the only thing you don't have is TD.
You've got 5 minutes.
Where?
It's in minutes.
Yeah.
So it's 4 times 60.
And it says every
Where's
T
TD
is
minutes?
not T.
T is measured in minutes.
Oh,
So
yes it is.
4 has to be-
So 4 has to be changed to minutes, which becomes times 60, 240. I don't know why I had a brain fart there. 240 minutes there. So, answering the question, you got N equals to N naught multiplied to 2 to the power of T over TD. Okay. We now know it's 100,000 times N naught, which is 5,000, times 2 to the power of 4 over TD. Okay? Oh, so not 4 again. 240,000. Yeah? 240. Sorry?
In the question at the start, in the question, will they give the full differential time or will we have?
Yeah, well, that's what I'm saying. I've never seen that in a exam before. Just this is only specific for your exercise.
So, but for example, if they did give that question to go for a stack question,
Yeah,
will the rule just be immediately included?
they would have to. Yeah, it can't assume because then so many questions would come out of like, well, how many cells does it split up to? They might even use E. There's too many sort of ambiguity to it. They would have to like tell you something. So they would have to say the cell splits up to 2 every minute or every 30 seconds, whatever it is, or T minutes. Then you have to be able to use that information to formulate this. In this particular case here, because it's an example and they've given you a preverb to it, you just go follow it. Okay, so in this case here, it's all about solving this issue, just inversing everything here. So we're dividing both sides by 5,000. And what's 100,000 divided by 5,000? 20, good. It's just like saying 100 divided by 5, okay? That's 2 to the power of 240 over TD. And the only way we know how to solve this problem is remove the base 2. And removing the base 2, we would log. Okay, you can all type this in your calculator at this point. You got log base 2 of 20 on each side is equal to 240 over TD. Therefore, TD has to equal to? Good. Excellent. 240 over log 2 of 20. Okay, type that in your calculator and whatever that answer is, that's your growth or generation time for the number of cells. So 2 cells for every X amount of minutes. Okay? Was that easy? Yeah? Pretty good? Now, next one. This is all in your textbook, by the way. I'm just trying to explain so that you can see what's going on there. Let's try this one here. What about this one? So this one now talks about after 1,000 years, a sample of radium-226, you can ignore that, a sample of something, okay, has decayed. So decayed is telling you it's a graph that's dropping down, so you know K is negative already, to 64.7% of its original mass.
Wow.
Okay? Find the half-life. So, let's stick with a few things. I've got 1,000. What is that representing? I've got 64.7%. What is that representing? And I'm trying to find half-life. Now, some of you don't do chemistry. What is a half-life? Anyone know? Nas? Or is it physics, is it?
Well, it depends on the substance.
Yeah, because it's half-life over. Isn't T measures the amount of time it takes for something to lose half mass?
That's exactly it. So for those who don't know what a half-life is, half-life just basically means how long, so it's a question of long, how long does it take before you get 50% of the original? Okay? What they've given you up here is how long it takes to have 64.7% of the original. Okay, but we don't want 64.7%. We want to know how long it takes for 50% of its original. Okay? So, what does 1,000 represent and what does 64.7% represent? That's what I want to know. And then how are we modeling this? So using the two things that I've shown you, and we've got an exponential model. 1,000 is A. Is that what you said? A or N. So here we go. We've got two models here. We had A naught, and then you got a base, which I'll call B to the power of KT. Okay? Or you can have N equals to N naught times, that was 2 in our example there, to the power of T over TD. Got two of those now. Which one would you use? Equation 1 or equation 2? Hands up for 1. Hands up for 2. Hands up for I don't know. In our case, we know it's not a cell division. Okay, so it can't be, and in this particular rule here, that was only given when we're talking about generation time and we're talking about cell splitting. We're not doing that with decaying. So it can't be this. It has to be the first one. The first one was talking about growth and decay. Now, what 100?
I mean 1,000.
1,000, yes. How do you know? When you say years, what is that representing? Is that an amount or is it a time? Time. Okay? When you have an amount, so if I talked about like money, or if I talked about number of bacteria or N or whatever it is, that's what it means. But years is time. So this has to be T, when T equals 1,000, so that's how long it takes. Okay, so 1,000 years, it's decayed to 64.7%. And this is the key part of its original mass. So I'll say it again, 64.7% of its original mass.
So would that be,
Yeah, that's the thing. It's in there later.
Let's think about the example I said about my laptop.
wouldn't 64.27 be A divided by A0 times 100?
64 is A.
So
64 is A, right?
64.7% is not A.
But it's
but
decayed.
A divided by A0
Decayed to, it's
times
true,
100.
but remember it's 64.7% of its original mass. Now, so that what that tells me is I don't know what the original mass is.
64.7x.
Yes, and that represents, as you said before, A. Okay, so not K. A is an amount. So A, you know this is 64.7%, which means out of 100 of X, which is, well, technically it's A naught because that's what you don't know the original mass, right? So A naught is what you started off with. And you're right, it said to 64.7%, so that's your final amount. But your final amount's not 64%. 64% just means 64 out of 100. What you want is 64 over 100 of the original. So the X is really your A naught. So what they've given you is they've actually just said 64.7% of A naught. That's what it's really saying. Or alternatively, if you don't like the way it looks, you could say 0.647 A naught. That's what your final amount is. Okay, so the final amount A is 64.7% of the original. Does that make sense? Yeah, the original I don't know. I don't know how much the original is. What would the base be? So I know T was 1,000. What would the base be? Anyone have a clue? What would the base be? It's not given. That's the clue. So if it's not given, you would use E. Okay, so if it's not given, you use E. It's okay. Yeah, you don't have to figure it out unless they tell you. Okay? Yep, so you can just use E. So in our case here, I've got a model now. I've got A, which is equivalent to 0.647 of A naught, is equivalent to A naught multiplied to E to the power of K times 1,000. Okay? So what are we trying to find here? K. Why do we want to find K? It gives us at least a rate. And right now we don't have an equation because our goal eventually is to find out half-life. You can't find out a half-life if you don't have an equation. Your job is to find the equation first before you can do a half-life. Okay? So, the 50% thing, we'll get to that later, but what we need first is the equation. Now what we notice is we can get rid of the A naught on both sides because if you divide both sides by A naught, they cancel out. You end up with 0.647 is equal to e to the power of k times 1,000. And now you can solve for k. How do I solve for k here? What would we do? Log, fantastic Aiden, so we log both sides, so log base e, 0.647 is equal to k times 1,000, but what we want is k, so therefore k must equal to, good, log e of 0.647 divided by 1,000, okay, because that's times. That's how we get k. Now if we got k, how does this help us to find half-life? What is half-life really doing? 0.5. See, the other one was 64.7% of the original mass. What we want is 50% of the original mass. So, we'd be doing, really, this is just, oh, wow, what happened? This is really just asking you to do this. 50% of A naught, which is really the same thing as saying 0.5 A naught. And you're doing the same things again. You've got 0.5 A naught, which is what you don't know. You don't know the A naught as well, times e to the power. Now you got k. You have k as log e of 0.647 divided by 1,000 times t. And that was your goal. Your goal was to find how long. So you want to find t. So from here, divide both sides by A naught. You got 0.5 equals to e to the power of log e of 0.647 over 1,000 t, and you do exactly what you did on this side again. Okay, so log e both sides times by 1,000 divided by log e 0.67. That gives you time. Type that in your calculator. We got it. Okay, so just fast forward the answer there. T should equal to, what's that? Log e of 0.5 times 1,000. So 1,000 log e of 0.5 divided by log e 0.647. Type that in your calculator. That tells you the time. Okay, and that's the half-life, 50% of A naught. How long it takes before it drops down to 50% of the original mass. Does that make sense? What I'm doing there? Okay, so you can see if you're not given the base, if you don't know what you're starting, it's not splitting, it's not doubling, it's not tripling, it's not dropping in any other way, then you don't know it. And if you don't know, it's fine. And the only thing we do was just 64.7% of the original. The original is what you're starting off with. Okay? So that's what this exercise is about. It's about you working out what kind of model I have and what the information is given to you to solve the problem. Okay? Now one last example, just to pay attention to something, because it happens at the end of year as well. And the only reason why you get it wrong, not because you model it wrong, but because you're reading it wrong. And that's the only thing I want you to pay attention to. So yeah, read this one. And the goal for me in this example is just to pay attention to one detail. So I want you to read, the population of a town was 8,000, and this is the key word, beginning of 2007, and then 15,000 at the end of 2017. So when it says find the population at the end of 2016, okay, I want you to think about,
What the hell?
I just want you to think about it. Why is it the beginning and the word end? Because it's a key fact for question 2. It says in what year, so you're trying to find time now, and it says population doubles that of 2014.
But the end and beginning.
Okay, I want you to think about it. So let's say 2014, they began 2007. How many years is it from 2007 to 2014? And that's the problem. See, a lot of kids, a lot of students will normally say it is 7, it is true, but remember it's beginning of 2007 to the beginning of 2014 is 7 years. But if you say the end of 2014 or end of 2016, it would then be 8 years because you've gone an extra 365 days.
Wait, is the beginning of
2014, the same as the end of 2013.
Yes.
Okay.
And that's the only thing. So if they do give you that, that's the only thing you got to pay attention to, why they put the word beginning and the word end. Okay, so if they said to find the end of 2016, okay, from 2007 to the end of 2016, it is not 16 minus 7, which gives you, what's that, 9 years. It's actually 10 years, because you go from 2007 beginning to 2016 beginning is already 9 years there, but you've gone an extra 365 days to get to the end of 2016. That's why that's an extra year. Okay, so that's 10 years. So that happens end of year when you're doing your exams. Most students only fail because of, not fail, but like to get the mark correct, is losing that T extra 1. And that's all I wanted you to pay attention. Everything else is the same. So you're modeling with A, naught, you're figuring out 2 unknowns because they've given you 2 pieces of information. They're giving 2007, 15,000, and then 2014 and 8,000. Yeah? So if you've got 2 pieces, it's likely you've got 2 unknowns to solve for. It's not hard to solve. What you have to do is the details. And that's what happens when you're doing your SACs and your exams. It's about details. Okay? But that's exercise 5I. How do we feel? Pretty good? No? It's all calc work, just rearrange and solve. But the problem is interpreting. Interpreting is key. Okay? But that's it. Thank you. Let me just